Hello students, I am Dr. Varun Mohan from ABES Engineering College, Ghaziabad. This is the second lecture of the lecture series of Unit 3 of Engineering Chemistry, BAS 101 and BAS 102. In the last session, we discussed about various concepts of electrochemistry, including the generation of electrode potential, its measurement with standard hydrogen electrode, and properties and applications of electrochemical series. Today, we shall discuss about some other concepts of electrochemistry. These are the contents of today's lecture. First, we shall define what is cell, and we will discuss about its various types. After that, we shall understand how an electrochemical cell is constructed and how does it work. We will compare the electrochemical and electrolytic cells together. And after that, we will understand the representation of an electrochemical cell. We will find out the functions of salt bridge, and then we will have a discussion on EMF of the cell. We shall derive the relationship between Gibbs free energy and EMF. After that, we shall derive Nernst equation and find out its applications. We shall find out the relationship between enthalpy and EMF. And at last, we shall solve certain numerical problems. So let us first define cell. A cell may be defined as a device which is used for the conversion of electrical energy into chemical energy or chemical energy into the electrical energy. So cells may be of two kinds. The first one is electrochemical cell or galvanic cell, or it is also called voltaic cell. These cells convert chemical energy into the electrical energy. The second category of cells are called electrolytic cells. These convert electrical energy into the chemical energy. As the name suggests, they utilize the electricity for the breakage of the chemical bonds, and this is how they convert and store the electrical energy in the form of chemical energy. Now let us understand how an electrochemical cell is constructed and how does it work. Electrochemical cell or a galvanic cell is a device which converts chemical energy from a spontaneous redox reaction into electrical energy. A typical example of galvanic cell is Daniell cell. The diagram or the picture of the Daniell cell is shown in the slide. We can see that the Daniell cell consists of a zinc electrode which is immersed in zinc sulfate solution. This is the electrode where oxidation takes place, and that's why it works as anode. It also has, this cell has a copper electrode which is immersed in the copper sulfate solution. This is the electrode where reduction takes place, and that's why it is called as cathode. These two half cells are connected with the help of salt bridge. Salt bridge is this inverted U-shaped tube which connects both half cells. It has an aqueous solution of an electrolyte that may be KCl, that may be KNO3, that may be K2SO4 as well, or some other electrolyte. Some gelatin or agar-agar is also added in this solution, in this electrolyte solution, to convert it to the semi-solid paste. Now, when these two electrodes are connected with the help of a wire externally, the reactions occurring in these two half cells may be shown as at anode, oxidation will occur. So it may be shown as zinc is oxidized to form zinc cation and 2 electrons are lost. So this is called as oxidation half cell. The oxidation half reaction. Oxidation half reaction. At cathode, copper 2 plus ions from the solution will take up the electrons and they will form copper solid. Because copper 2 plus ions are reduced here, this reaction is called reduction of reaction. So the net reaction may be shown as zinc solid copper ions in solution. They react with each other. Here, 2 electrons are on the product side and 2 electrons on the reactant side. So those will cancel out. And it will be zinc underwent oxidation and copper underwent reduction. So this is the complete cell reaction. These are half cell reactions showing oxidation and reduction, and this is the complete cell reaction. So overall process is shown here in the picture. This is the Daniell cell. This is zinc electrode. This is copper electrode, and zinc is undergoing oxidation. So this is the zinc rod surface, and zinc is losing 2 electrons. It is this rod is retaining these 2 electrons, and zinc is forming the Zn2 plus ion. Because it is now having the charge, it goes into the solution and electrons are retained on the rod. So this electrode, the anode, becomes the negative. Because zinc 2 plus ions are going into the solution, to maintain the electrical neutrality, anions from the salt bridge reach into the oxidation half cell. Similarly, copper rod also participates in the reaction, but here the 2 electrons which reached to the copper rod from the zinc rod, those are taken up by the copper ion solution, copper ions present in the solution. So these cupric ions take the electrons and get themselves reduced. So it forms the solid copper and deposits at the surface of the copper rod. So 2 electrons are taken up by the cupric ion and it takes up these electrons to form the solid copper. Now, because copper 2 plus ions are getting reduced and deposit at the surface of the copper rod, so the cations become less in the solution, and to maintain the electrical neutrality, these cations from the salt bridge reach into the reduction half cell. This is how the electrochemical cell works and the current flows in the cell. Now we shall compare the electrochemical cell with the electrolytic cell. This is the representation of the galvanic cell on the left side of the slide, and on the right side, electrolytic cell is shown. We can see in galvanic cell, we have 2 different salt solutions, and both of these containers represent the half cell. The anode is dipped in the oxidation half cell and the cathode is dipped in the reduction half cell. Both half cells are connected with the help of a bridge, that is salt bridge, and both electrodes are connected externally with a wire. Because oxidation is occurring at the anode, electrons are retained with the anode, so it becomes negative, and because the electrons are being taken up from the cathode, so it becomes positive. In case of electrolytic cell, we can see that there is a single solution in which both electrodes are immersed. These electrodes are connected to the positive and negative terminals of the battery. Positive terminal is connected to the anode, and because it is having less electrons, it is acquiring the positive charge here. And because of positive charge, it causes oxidation of the species. On the other hand, the electrode which is connected to the negative terminal of the battery, that is having excess of electrons, and it causes reduction of the species. So here, anode is having the charge positive and cathode is having the charge negative, which is opposite to that found in case of the electrochemical cell. Now we will summarize the differences between galvanic cell and the electrolytic cell. Electrochemical cell and electrolytic cell. And now we will find out the differences. As we have already discussed, electrochemical cell converts the chemical energy into the electrical energy. So it is chemical energy into the electrical energy. On the other hand, in electrolytic cell, there is conversion of electrical energy into the chemical energy. Since the chemical energy is itself converting to the electrical energy, it means the reaction should be spontaneous in case of electrochemical cell. So here at the electrodes, spontaneous reactions take place. So spontaneous reactions take place. In electrolytic cell, there is no change until we conduct the electricity. It means that the reactions are not occurring by themselves. It means that the reactions are non-spontaneous. So here, reactions are non-spontaneous in nature. In electrochemical cell, there should be a potential difference between the two electrodes so that a spontaneous reaction may occur. For it, there must be two dissimilar electrodes. So the electrodes here are of dissimilar metals. In electrolytic cell, the electrodes may be made up of the same metal or maybe of different metal. So here, those may be of same or different metals. In electrochemical cell, electrolyte is basically the solution of the ions similar to that of the electrode. So here, each electrode is dipped in the electrolyte solution of its own ions. Whereas in electrolytic cell, both the electrodes are inserted in the same electrolytic solution. So those have same electrolyte solution. Because here we have two different half cells, those have to be connected with the help of salt bridge. But in electrolytic cell, we don't have different half cells. We have a single solution, so salt bridge here is not needed. So in electrochemical cell, we need salt bridge. It is needed. Whereas in electrolytic cell, salt bridge is not needed. In electrochemical cells, anode is the negative electrode and cathode is positive electrode. Whereas in electrolytic cell, sign conventions are just opposite. So here we have anode as positive electrode and cathode as negative electrode. So these are the differences between electrochemical and electrolytic cell. Now we shall understand how to represent the electrochemical cell on a paper. There are certain rules which have to be followed to represent an electrochemical cell on the paper. The first is that anode is always shown on the left side. Anode is the electrode where oxidation takes place. So anode is always shown on the left side, whereas cathode is always shown on the right side. Anode and cathode are both separated by two vertical lines which represent salt bridge. When we represent anode, we first write the metal and then we write its electrolyte solution separated by a vertical line. When we write cathode, we have to write first the metal ion. So if we write it as M1 and M2, so if it is M1, this is the cation of M1. And if this is M2, so we have to, in case of cathode, we have to first write the cations, the ions of the metal, and after that it has to be separated by a vertical line with the metal. So in case of anode, we write first the metal and then the ion separated by a vertical line. And in case of cathode, we first write the ion, the electrolyte, separated by the metal with the help of a vertical line. And anode and cathode both are separated by two vertical lines, which represents the salt bridge. So anode is responsible for the oxidation. So this is oxidation half cell. And cathode is responsible for the reduction. So it represents the reduction half cell. So we can represent the Daniell cell as it is in solid form ZnSO4. Here we write the concentration. This is salt bridge. Then here we write the concentration. And then, so this is anode. And this is cathode. and it represents the salt bridge. We may also write it as it has to be remembered that when same electrolyte is used in the half cells, then no separation is shown. For example, we can represent this cell platinum, hydrogen at 1 atmospheric pressure, then the electrolyte 0.1 molar concentration, then Cl2, and then platinum. So here we have the common electrolyte, the same electrolyte, HCl, and HCl is the electrolyte here which provides H plus ion in the hydrogen electrode. It provides H plus ion to the hydrogen electrode and Cl negative ions, chloride ions to the chlorine electrode. So when we have same electrolyte for both half cells, then in that case, the representation is like this. At this point, we have understood how does an electrochemical cell work and how to represent it. So we can summarize the functions of the salt bridge. So salt bridge is that inverted U-shaped tube which has porous plugs at the end and it has an electrolyte filled inside along with the agar-agar or gelatin which converts the electrolyte solution into a semi-solid paste. So there are three major functions of salt bridge. The first one, it completes the circuit. It completes the circuit. Second, it prevents the intermixing of the solutions of the two half cells. It prevents the intermixing of the solutions of the two half cells. And third, it maintains the electrical neutrality in both the solutions. For example, it can be understood by this picture. This is the salt bridge where we have zinc anode and the tin cathode. So when zinc is oxidized, it generates Zn2 plus ions which go into the solution. And because cations are increasing in the solution, anions have to reach from the salt bridge to the electrolyte solution, to the oxidation half cell solution, so that they can be counterbalanced. So this is how it maintains the electrical neutrality. Similarly, in the reduction half cell, when Sn2 plus ions are getting reduced, their number decreases in the reduction half cell. So to counterbalance the uh, number of cations, the K plus ions, potassium ions reach from the salt bridge to the reduction half cell. This is how it maintains the electrical neutrality. So it maintains the electrical neutrality in the half cells. So this is about the salt bridge. At this point, we can easily understand what is EMF of an electrochemical cell. EMF refers to it represents the electromotive force. EMF is the electromotive force. It is also called the cell potential. So it can be defined as the EMF of an electrochemical cell is the maximum potential difference between two electrodes of a cell. The maximum potential difference which can be obtained between two electrodes of an electrochemical cell, that is called EMF. So we generally represent it as E. So E cell may be shown as E cathode minus E anode, because it is the maximum potential difference between the two electrodes of the cell. Because cathode is always shown on the right and anode is always shown on the left side, so it can also be written as E cell equal to E right minus E left. It has to be remembered that the cell reaction of an electrochemical cell is feasible only when the E cell has the positive value. So positive value of E cell shows the spontaneity of the reaction in the electrochemical cell. Thus, for the galvanic cell, we can show it as, if it is the cell, zinc solid, it is aqueous, then salt bridge, aqueous in contact with copper. So here, for this cell, this is the galvanic cell, specifically the Daniell cell. So for this cell, EMF can be calculated as E cell equal to E Cu2 plus to copper, the reduction potential of the cathode, minus E Zn2 plus converting to Zn. This is the reduction potential of anode. We know in the cell representation, this is the cathode and this is the anode. So EMF of the cell becomes reduction potential of copper electrode minus reduction potential of zinc electrode. Now we shall find out the relation between Gibbs free energy and EMF of the cell. In a galvanic cell, the electrical energy produced is equal to the product of its EMF and quantity of electricity which passes through it. It means we can write it as net electrical work done is equal to Q multiplied by E, where Q is expressed in Coulomb. It is the quantity of electricity passed through it. So it is in Coulomb. And E is the EMF of the cell. It is expressed in volts. So Coulomb volt is equivalent to the joules. But we know, according to Faraday's law, according to Faraday's law, Q can be expressed as NF, where N is the number of electrons associated with the chemical change, and F is the Faraday constant. So N is the number of electrons, and F is Faraday's constant. Substituting this value here, it becomes net electrical work done is equal to, so Q becomes NF multiplied by E. It means it is NFE. But according to Gibbs and Helmholtz, the electrical energy of a reversible cell is given by the free energy decrease of the reaction occurring in the cell. So if free energy decrease minus delta G is equal to the net electrical work done, net electrical work done or net electrical energy produced it will be equal to NFE. It means we can say minus delta G equal to NFE. So this is the relation between Gibbs free energy change and EMF of the cell under standard conditions. So under standard conditions, this equation becomes as minus delta G not equal to NF E naught. So we can relate the Gibbs free energy change under standard conditions with the electrode potentials under standard condition. As we have discussed that in the electrochemical series, all the potentials are measured under standard condition. But in practical cases, the experiments are not done always under the standard condition. So how can we get the potential values under those conditions which are different from the standard conditions? For this, we need Nernst equation. This is the Nernst equation, and Nernst equation is E equal to E naught minus 2.303 RT upon NF log A product upon A reactant. This A represents the activity of the product, and here A represents the activity of the reactant. So here E is equal to the electrode potential E naught is equal to the standard reduction potential, or we can say standard electrode potential, standard electrode potential. R here is the gas constant T is the temperature on Kelvin scale. N is the number of electrons associated with the reaction. And A here represents the activity. At this point, we should know what is activity. Activity is a measure of the effective concentration of any species in a solution, which accounts for the non-ideal behavior due to interaction among the particles. So it is basically the effective concentration of any species. Now we will derive the Nernst equation. So this Nernst equation tells us the effect of electrolyte concentration on electrode potential. To derive it, we can consider a general electrode reaction, that is Mn plus it takes up n electrons to form M solid. As we have discussed in the previous session, that all the reactions in the electrochemistry are conventionally shown as the reduction reaction. So we are showing this reaction as a reduction reaction. For this reaction, Gibbs free energy change can be calculated as delta G equal to delta G naught plus RT ln activity of products upon activity of reactants. But we know that delta G is equal to N minus K N Fe. Delta G is equal to minus NFE, and delta G naught will be equal to minus NF E naught. So if we substitute these values here, it will become minus NFE equal to minus NF E naught plus RT ln activity of products upon activity of reactants. Dividing this equation by minus NFE, so we divide it by minus NF, it will become minus NF E upon minus NF equal to minus NF E naught upon minus NF plus RT ln RT upon minus NF ln A products upon A reactants. For the sake of simplicity, we are writing P as a symbol for products and R as a symbol of reactants. So it becomes as E equal to E naught minus RT upon NF ln activity of products upon activity of reactants. Here E is the electrode potential, E naught is the standard electrode reduction potential, and R is here the gas constant, T is the temperature in Kelvin, N is the number of electrons associated with the chemical change, F is the Faraday constant whose value is 96500, that is 96,500 approximately, and AP represents the activity of the product and AR represents the activity of the reactant. So at 298 Kelvin, we can calculate these values as E equal to E naught R is 8.314 multiplied by T is 298 upon N. F is 96,500 ln activity of product upon activity of reactants. We can convert it to the log of base 10. In that case, it will be E equal to E naught minus 8.314 multiplied by 298 multiplied by 2.303 divided by N multiplied by 96500 log activity of products upon activity of reactants. So after calculating these constants, the value becomes as E equal to E naught minus 0.0591 upon N log activity of products upon activity of reactants. At this point, we should know that in dilute solutions, the activity of any species does not differ much from its concentration. So we can take the concentration terms here in place of activity. So it becomes as E equal to E naught minus 0.0591 upon N log product, the concentration of product upon the concentration of reactants. The product here is metal solid and the reactant here are the metallic ions, metallic cations in the solution. So we will replace them with their concentrations. So it becomes as E equal to E naught minus 0.0591 upon N log metal in the solid form divided by concentration of metal and plus ions in the solution. For pure solids, the concentration term is always unity. So for pure solids, like this, the solid metal, the concentration term is always unity. So if we keep it here, it becomes E equal to E naught minus 0.0591 upon N log 1 upon concentration of the metal ions in the solution. So this equation is called the Nernst equation. Basically, it can be used for calculation of electrode potential. Here we can see two things, that the electrode potential E increases when the concentration of Mn plus ions increases, because once it increases, this term will be lesser in its value and the potential will increase. The second thing which we observe is that if the temperature of the operating conditions it increases, in that case the E value will decrease, because once it increases, this term will decrease in the magnitude and the potential will decrease. Now we shall derive the Nernst equation for the cell. So for the cell, suppose this is the reaction representing this reversible reaction in the cell. AA plus BB converts to CC plus DD. In that case, Nernst equation may be written as E equal to, here we will write E cell equal to E naught cell minus 2.303 RT upon NF log concentration of products upon concentration of reactants. So here we have products C. The stoichiometric coefficient are raised as exponent. So it comes as a small c, d, and then a small d divided by concentration of A raised to the exponent small a and B raised to small b. So with the help of this Nernst equation, we can determine the electrode potential of the cell at any given temperature. Now where can we apply the Nernst equation? It is used for the determination of potential of electrodes. We know Nernst equation is E equal to E naught minus 2.303 RT upon NF log concentration of products upon concentration of reactants. So if we know other values, we can calculate the potential of the electrode. Similarly, we can calculate the potential of the cell if we know the standard reduction potential of the cell. If other values are known, we can calculate the concentration of the ionic species. The concentration of ionic species depends upon the solubility of the species. So if we know the concentration of the ions, we can easily calculate the solubility of sparingly soluble salts. In the denominator, we see that there is the term N, which represents the number of electrons participating in the reaction. So the valency of ion can also be calculated with the help of Nernst equation. The pH of the solution depends upon the concentration of H plus ions. So it can also be used to calculate the pH of the solution if H plus ions are involved in the cell reaction. The E value represents the feasibility of the reaction. If it is positive, then it will show the spontaneity of the reaction or the feasibility of the cell reaction. Now we can calculate the relationship. We can find out the relationship between enthalpy and EMF of the cell also. From the thermodynamic understanding, we know that delta G is equal to delta H minus T delta S. But we know that at constant pressure, Gibbs Helmholtz equation shows minus delta G is equal to minus delta H minus T derivative of delta G with respect to temperature at constant pressure. Here, the minus delta H represents the decrease in the enthalpy of the cell reaction at constant pressure. So if we substitute the value here, as we know minus delta G is equal to NFE, so it becomes NFE is equal to minus delta H minus T derivative of minus NFE with respect to the temperature at constant pressure. Here N and F both are constant, so it becomes as NFE equal to minus delta H plus TNF derivative of E with respect to the temperature at constant pressure. Now we can divide it by NF. So it becomes NFE upon NF equal to minus delta H upon NF plus TNF upon NF derivative of E with respect to temperature at constant pressure. So it becomes E equal to minus delta H upon NF plus T derivative of E with respect to temperature at constant pressure. Now this value is the temperature coefficient of the cell. We can write it here. It is the temperature coefficient of the cell. We can also calculate delta S from here. So to calculate the delta S, we should know that we have derived it here. Minus delta G, that is equal to NFE. So minus delta G is equal to minus delta H plus TNF derivative of E with respect to temperature at constant pressure. So we can rearrange it as delta G equal to delta H minus T NF derivative of E with respect to the temperature at constant pressure. But we know that delta G is also equal to delta H minus T delta S. So on comparing, we find that delta S is equal to NF derivative of E with respect to the temperature at constant pressure. This is how we can calculate the delta S value. Now we will see a few questions which have been asked in previous year examinations. The question 1, give the construction and working of the galvanic cell. And question 3, discuss the principle and working of a galvanic cell. Those have already been discussed here in this slide. So here we discuss the electrochemical cell and its construction. And here we discussed its working. To summarize it here, we can say that electrochemical cell is the cell which converts chemical energy into electrical energy. It has two half cells. One is oxidation half cell, another is reduction half cell. And here the zinc electrode is immersed in a solution of its own ion and it works as anode. Oxidation occurs here and the electrons are accumulated on this metal rod. These electrons move to the cathode through the external wire, and these electrons are taken up by the cupric ions in the solution, which get reduced. So this is how electrons move from anode to cathode. The electron neutrality is maintained by the salt bridge here. What is salt bridge? Mention its function. Question number 2, what is salt bridge? Mention its function in electrochemical cell. Salt bridge is an inverted tube, which has already been discussed here in the previous slide. This one. So salt bridge is an inverted U-shaped tube which connects the two half cells in the electrochemical cell. It has three major functions. First, it completes the electric circuit between the two half cells. Second, it prevents the intermixing of these two solutions. And the third one, it maintains the electron neutrality in both half cells. Now we shall discuss a few numericals here. What is the potential of the half cell consisting of zinc electrode in 0.01 molar zinc sulfate solution at 25 degrees centigrade, given standard electrode potential is minus 0.763 volt. So we are having E naught equal to minus 0.763 volt. Temperature is equal to 25 degrees centigrade. That is 25 plus 273. So it is equal to 298 Kelvin. And we have zinc 2 plus ion concentration from zinc sulfate, that is equal to 0.01 molar. We have to calculate the potential of half cell, so we need Nernst equation here. Nernst equation is equal to E equal to E naught minus 0.0591 upon N log concentration of products upon concentration of reactants. We know for this electrode, for the zinc electrode, it will be zinc 2 plus 2 electrons converts to zinc solid. Remember, the reactions are always shown as the reduction reaction. So here we have the value E naught as minus 0.763 minus 0.0591 upon N. Here we have 2 electrons, so N is equal to 2 log product upon reactant. Product we have zinc solid, and for the zinc solid, the concentration term will be unity divided by reactant. Reactant is the zinc ion concentration. So zinc ion concentration is 0.01 molar. So if we calculate it, it will be minus 0.763 volt. minus 0.0591 upon 2 log 100, or we can write it as minus 0.763 minus 0.0591 upon 2 into 2 log 100 is equal to 2, because 2 log 10 will be equal to 2 multiplied by 1. So it is minus 0.763 minus 0.0591. It cancels out. So it is equal to minus 0.822 volt. Next question. Calculate the EMF of the cell. Cell is given here. Write the cell reaction. The standard EMF of the cell is 1.54 volt. So first we write the reaction at anode. The reaction will be zinc solid converting to zinc aqueous 2 plus ions plus 2 electron. At cathode, this is the cathode on the right hand side. So it will be Ag plus will take up electron to form Ag solid. But it is only one electron reaction. To balance it, we have to multiply it by 2. So that the number of electrons on the product side and on the reactant side become equal. So net reaction is zinc solid plus 2 Ag plus convert to zinc 2 plus aqueous plus 2 Ag solid. So this is our cell reaction. The standard EMF of the cell is given, that is 1.54 volt. We have to calculate the EMF of the cell. So we need the Nernst equation. So according to Nernst equation, E cell equal to E naught cell minus 0.0591 upon N log concentration of products upon concentration of reactants. So we can write it as E cell equal to minus, so E cell equal to E naught cell minus 0.0591 upon N log. So products we have Zn 2 plus and silver raised to the power 2. Reactants are Zn solid and silver plus ion raised to the power 2. Here the solid terms, the terms which represent the solid species, those will be unity. So the equation reduces to E cell equal to E naught cell minus 0.0591 upon N log Zn2 plus upon Ag plus का whole square. Now we will place the concentration terms given in the solution here. So it will be equal to E naught is given as 1.54 volt. So it will be 1.54 minus 0.0591 upon n is the number of electrons. So there is 2 electrons change. It will be 2 log concentration of Zn2 plus is given as 0.2 molar. So it is 0.2 divided by concentration of Ag plus is given as 0.002 molar. So when we calculate it, it comes as E cell equal to 1.54 minus 0.0591 upon 2 log 0.2 divided by 4 multiplied by 10 to the power minus 6. So it comes as 1.54 minus 0.0591 upon 2 log 5 multiplied by 10 to the power 4. It means it is 1.54 minus 0.0591 upon 2 log 5 plus 4 log 10. So that is equal to 1.54 minus 0.0591 upon 2 log 5 is 0.698 plus 4 multiplied by 1. So it is 1.54 minus 0.0591 upon 2 multiplied by 4.698. So it comes as 1.54 minus 0.138, that is equal to 1.402 volt. Next question. Write half cell and net cell reactions of the galvanic cell at 25 degrees centigrade. Cell is given here. Find the EMF of the above cell. The electrode potentials of anode and cathode are given. Standard reduction potentials of anode and cathode are given here. So first we will write the reactions. So at anode, it is zinc. This is anode on the left side. So it is converting to Zn2 plus aqueous plus 2 electrons. This is the oxidation half reaction. At cathode, copper 2 plus aqueous is taking up these 2 electrons to convert to copper solid. These cancel out. So net reaction becomes zinc solid plus copper 2 plus aqueous convert to Zn2 plus aqueous plus copper solid. Now we have to calculate the EMF of the cell, but we know EMF can be calculated as E cell equal to E cathode minus E anode. Cathode here is on the right hand side, that is copper, and for copper the electrode potential, standard electrode potential, is given as 0.34 minus, for anode it is given as minus 0.0591. 0.76 volt. So it comes as 1.1 volt. This is the standard EMF of the cell. EMF of the cell under standard conditions. Now we have to calculate the EMF of the above cell. For this we will need the Nernst equation, and Nernst equation is E cell equal to E naught cell minus 0.0591 upon N log product upon reactants. So E cell we have calculated already. That is 1.1 minus 0.0591 upon N is the number of electrons, which is 2 in this case, log product side. On product side we have solid copper, which has the concentration term as unity, and Zn2 plus. So here we will take Zn2 plus divided by reactants. Reactants here, this is zinc in the solid form, so its concentration term is unity. So we will not take it, and we can ignore it, and we will take Cu2 plus. So it becomes as it becomes as 1.1 minus 0.0591 upon 2 log zinc 2 plus and copper 2 plus both have 1 molar concentration, so it comes as 1 upon 1, and we know log 1 is 0. So if it is 0, the whole term becomes 0, and the value becomes E cell equal to 1.1 minus 0. So it comes as 1.1 volt. Next question. Give significance of Nernst equation. Consider a cell reaction. Cell is given here. Standard reduction potentials of Zn2 plus and Cu2 plus are given here. Write half cell reactions, complete cell reaction, and calculate EMF of the cell. So we can calculate first E naught cell will be equal to E naught cathode minus E naught anode. So it will be, for cathode, it represents the copper, and anode is shown on the left, so it is the zinc electrode. So we can place their values here. That is E Cu2 plus 2 Cu minus E naught Zn2 plus 2 Zn. It means it will be 0.34 minus 0.76, that is 1.1 volt. Now if we have to write the reactions at anode, that is on the left side, so it is zinc. Zinc is undergoing oxidation to form zinc 2 plus in the solution and loses 2 electrons. At cathode, that is on the right side, so it forms Cu2 plus, taking 2 electrons converts to Cu solid. So the net reaction is zinc solid plus copper 2 plus in aqueous form converts to zinc 2 plus in aqueous form plus copper solid. Now we have to find out the EMF of the cell, and we have E naught value with us. So we need Nernst equation. So E cell will be equal to E naught cell minus 0.0591 upon number of electrons, that is n, log product concentration upon reactant concentration. E naught cell we have calculated, that is 1.1 volt minus 0.0591 upon n is the number of electrons, that is 2 here, log product. Product we have zinc ion and copper solid. Solid species have pure solid species have the concentration term as 1, so we can ignore it and it becomes Zn2 plus divided by the reactant. In reactant here the zinc is solid, so it will have the concentration term as unity, so we can ignore it and it will become Cu2 plus. So after placing the values here, 0.0591 upon 2 log, it comes as 0.1, that is the concentration of zinc, divided by copper 2 plus ion concentration is 0.2 molar. So it becomes 1.1 minus 0.0591 upon 2 log 1 upon 2. So the value comes as 1.1 minus 0.0591 upon 2 multiplied by 0.3010, and that comes as negative value. So it will be 1.1 plus 0.008. So the final answer is 1.108 volt. Now the next question. The EMF of the cell is given here, involving following reaction. Reaction is given, and this is the EMF of the cell at two different temperatures. Calculate delta H, delta G, and delta S at 25 degrees centigrade. So here we can take T1 as 0 degrees centigrade, that is 273 Kelvin, and T2 as 25 degrees centigrade, that is 25 plus 273, that is equal to 298 Kelvin. E1 is 0.6915 volt and E2 is 0.6753 volt. Now we can calculate the temperature coefficient. So temperature coefficient is derivative of E with respect to T at constant pressure. So we can calculate it as E2 minus E1 upon T2 minus T1, that is 0.6753 minus 0.6915 divided by 298 minus 273. So it comes as minus 0.0162 divided by 25. Or if we calculate it, it comes as minus 0. Sorry. It comes as minus 6.48 multiplied by 10 to the power minus 4 volt per Kelvin. For this question, we have n equal to 2 because cadmium is converting to cadmium 2 plus, and in cathode, silver plus is converting to silver. So overall, there is 2 electrons change, and n here will be 2. This 1 electron change will be multiplied by 2 to balance the anodic half cell, the oxidation half cell reaction. So n is equal to 2 and F will be equal to 96500. Now we have to calculate delta G. So delta G will be equal to minus NFE, and N we have 2, so it is minus N is 2 multiplied by F we know, that is 96500, and E is 0.6753 because we have to calculate at 25 degrees centigrade. So we will take the respective potential value. So that is minus 1.30 into 10 to the power 5 joule per mole. Now we have to calculate delta S. We know delta S equal to NF derivative of E with respect to temperature at constant pressure. So that is equal to 2 multiplied by 96500 multiplied by minus 6.48 multiplied by 10 to the power minus 4, which we have calculated earlier. So it comes as minus 125.064 joule per Kelvin mole. If we have to calculate delta H, then it can be calculated as delta H is equal to delta G plus T delta S. So delta G we have calculated here. It is minus 1.30 multiplied by 10 to the power 5 plus T is 298 because we have to calculate at 25 degrees centigrade, and delta S we have calculated as minus 125.064. So it comes as minus 1.30 multiplied by 10 to the power 5 minus 0.372 into 10 to the power 5. So it comes as minus 1.672 into 10 to the power 5 joule per mole. So these were the numericals based on Nernst equation. These are some of the suggested references. Thank you for attending this session.